Anyway, so let me begin with a construction. So this, I've alluded to this a few times, and something also like this was also alluded to by Christine. So let's say that we have G as a group. And let's assume that we have K is a normal subgroup of G. And let's assume that Q is equal to the quotient G mod K. So i.e., we have an extension. 1 goes to K, goes to G, goes to Q, goes to 1. Of course, K is the kernel and Q is the quotient. That's why the letters are chosen. And so then, so each homology group HD of K has a Q action. So we get an action of Q on the homology groups of this group K. And let me give you two constructions of this. So let me give you a version, an explanation of this that's algebraic and an explanation of this that is geometric. So the algebraic well, so G, of course, acts on K by conjugation. And homology is a functor, so this gives us an action of G on the homology groups of K. But, and now this is something I think Christine said this quietly, that inner automorphisms, conjugation, a group always acts by conjugation on itself, but that induces the trivial action on homology. So K, acts on HD of K trivially. You should expect something like that to be true. So what is conjugation sort of fundamental? Conjugation is like changing a base point, right? And homology should know nothing about base points. And so therefore, sort of changing a base point shouldn't do anything to homology, and so we should get a trivial action. This is, inner automorphisms that trivial homology. You can prove, from any definition you know of group homology, you can prove this. And so thus we get, an induced action of Q on HD of K. That's the sort of algebraic explanation of where this action comes from. Let me give you a more a geometric one. So let's let X is equal to a K G1, and let's let X tilde to X. This is the cover associated to K, right? And so what can we say about that cover? So we can do that because, the fundamental group of X is G, and every subgroup of the fundamental group corresponds to some cover. This is a regular. So G mod K is equal to Q cover. So the action of Q on X tilde, that induces an action of Q on the dth homology group of X tilde, which is the same thing because X tilde is a K pi 1 for K as the homology of K. OK, so that's this. Now, I should say, it's not 100% obvious that this gives you the same action, right? And so you might, when you first see this, you're like, of course, obviously these must be the same thing. But if you think about it, I just want to leave you with the puzzle to prove this by yourself. So, so the inner automorphisms, so G acting by conjugation on K, that means that it puts G into the group of automorphisms of K. So by K pi 1 theory, since X tilde is a K pi 1, we get that each of these inner automorphisms induces some base point preserving map from X tilde to itself, just by the correspondence between group homomorphisms and homotopy classes of maps. And that's the one that induces this. But the deck transformations are not base point preserving. And so a priori, these could be two different actions. But in fact, they are the same. It's an extremely enlightening thing to prove that this action by deck transformations is homotopic to the action you get by K pi 1 theory. Okay? You have to sort of homotope it to move the base point back to itself in a consistent way. Anyway, so this is a basic construction. It shows up in many places. Let's apply to the situation that we're interested in, which is the Torelli group. Let's apply to the extension 1 goes to the Torelli group. Again, my boundary components go in the superscript. I'm sorry, I can't change. That's the Torelli group is a subgroup of the Teichmuller modular group, or the mapping class group. Was that funny? Like, I have jokes, and I didn't think that was one of them. So, and that's the quotient is the symplectic group sp2gz goes to 1. So we get an action of sp2gz. Well, on the homology of the Torelli group, each homology group, and I can put any coefficients I want here. I was doing everything as integer coefficients, but just for concreteness, let's put q there. I could put any coefficients I want. Okay? And so in other words, this right here is a q vector space with an action of the symplectic group sp2gz, i.e., this is a representation of the group sp2gz over q. Okay, so so each homology group of the Torelli group is a representation of the symplectic group. Now, we don't know anything, like, remember, these things are often infinite dimensional. So this is often infinite dimensional. So what can we say? I have to now describe the representation theory of the group sp2gz. So there's no hope of saying anything non-trivial about the infinite dimensional representation theory of the symplectic group. It's just too hard. Like, it's a sort of wild problem. You just don't expect there to be, there's some problems in math that you think we don't know the answer to because we're not smart enough, and there's some things in math that we don't know the answer to because there probably is no good answer, right? And this is the kind of thing, the naked infinite dimensional representations of an infinite discrete group are probably a gigantic mess about which you can say nothing. So we know even less. So I should say, like, the modular representation theory of this is even worse. We actually don't know it very well. I only know the characteristic zero representation theory of these groups. It seems, in modular case, seems much harder. Yeah. Oh, the congruent subgroup? Yeah. So we know things about that. That's a sort of with Z mod P coefficients. That's right, yeah. Yeah. And we actually do know things about that. So this is a theorem. This is a different theorem I could be talking about. This is a theorem of myself that in a stable range, if we take Q coefficients, that's the same as the homology of the whole mapping class group. So if we're taking, we're looking at these sort of level P congruent subgroups of the mapping class group, passing in them does not change the rational homology in a stable range. So that's so there's the representations are all trivial in that case. That would be that would be a long lecture series about the trivial representation. So, which I'm not above doing, but I'm not going to do. But that's somehow a different story. So, yes. Yeah. Right. Yeah. Right. And that's why we have symplectic group. With one function, we don't really have. We do, though. So, and the reason for that is that a little observation is that the homology of this, well, if you only have one boundary component, so yeah, well, no, you don't need primitive. This thing right here is literally the same thing as H1 of sigma g. because the boundary component's not it gives a trivial homology class. And so the intersection pairing on this, if we put rel boundary, like whatever, it doesn't change anything, right? It's the same homology. So we still get the symplectic group in that case. Yeah. Any other questions? If we had two boundary components, and next lecture we will have two boundary components at some point, then things are more complicated. You have to say what you actually mean by the Torelli group. So that'll show up later on, sort of, to prove things about the Torelli group on surfaces with 1 or 0 boundary components. Any other questions? You'll see why I need one boundary component later on. It'll make some statements cleaner and easier to state. So, OK. So what's the representation theory of the integral symplectic? It's actually quite hard. And so this is totally intractable. If G is equal to 1, since it's almost a free group. I can't say anything about the representation theory of a free group. How do you give a representation of the free group on n generators? You just give me n matrices, right? I mean, there's no structure. It's too unstructured of a group. And so we really need, so let's assume that G is at least 2. That puts us in a situation called the higher rank situation, in which these groups have more internal structure, and we actually can give a very complete picture of their representation theory, remarkably. OK, so let's fix, so a field, which I'll write as F right there. And so there's two basic kinds of F finite dimensional. F reps, OK? So the first kind are the algebraic ones. So the algebraic representations. So these, what are they? These are actually representations of the algebraic group. These are, so we take, so a polynomial representation of the algebraic group SP to G F, and we restrict to SP to GZ. Now that sounds scary as an algebraic representation of the algebraic group, but in fact all the representations that you probably would think about are probably of this form. So these are actually very familiar representations. So for example, F as ker, field F, that's right. Oh, I forgot to say that, yes, ker of F is equal to 0. It's very important. So therefore, the integer points are actually, F contains Z, right? So, OK, so here is some examples of this. These are just the basic examples. For instance, you could take something like H, which is the first homology group of your surface with F coefficients. So that's F to the 2G with the sort of standard action of F. That's such a thing. You could take, like, I don't know, tensor powers of that. You could take exterior powers of H, symmetric powers of H, etc. Right? There's many, all the sort of standard sort of linear algebraic representations that are derived from sort of basic linear algebra from H, and using the symplectic form are of this flavor. And by the way, so I said these are polynomial representations. What that really means is that the entries of these, a representation gives a matrix for every element of sp2gz or sp2gf. And what this is saying is that the entries of those matrices are polynomials in the entries of sp2gf. And that's like, here, like, they are literally the matrix entries. Here, they're like, you can work out what they are for the exterior powers and the tensor powers and so on. So these are the basic things right there. So these are in bijection with representations of the Lie algebra, so which my ability to write fractor letters is not that great, but that's the best I can do. Those aren't actually that. OK, that's whatever it is right there. You can and they were classified. So F is algebraically closed, you know, by Cartan, I think. So in the early 20th century. So this is one of the sort of early sort of triumphs of algebraic group theory or Lie theory. You know, CF, you know, if you ever read any book on the representation theory of semi-simple Lie algebras, CF, you know, the sort of canonical place we send graduate students is full to read about these things. So these are extremely well understood. And they're probably the representations that I think many of you have encountered in your day-to-day life. Okay? Note to me, there's like some basic things you might ask. So for instance, you know, if these representations are irreducible, do they remain irreducible when we restrict to sp2gz? And the answer is yes. So nota bene, so an algebraic rep V is irreducible on you know, sp2gf, so it has no non-trivial subrepresentations, it's also irreducible on its subgroup sp2gz. That's not a 100% trivial fact. This is what follows from what's called the Borel density theorem, which says that this group right here is Zariski dense inside sp2gf. So you know, anything that involves polynomials, if it, you know, saying you're irreducible says that, you know, we're saying that irreducible says you can choose a basis so that your block matrices, right? So there's some zeros in the block matrices. Those are like polynomial conditions. And so if those things are 0 on the integer points, they're also 0 on the whole thing. So things like that. So there's so the sort of Fulton-Harris picture of the polynomial representations of the Lie algebra is faithfully reflected in the representation theory of sp2gz. Yes? Yeah. Well, yeah. That's right. If it's absolute, but even if it's, you don't even need that. So that's a stronger condition, right? Because like there's things that are irreducible, like they're not geometrically irreducible, right? Or absolutely irreducible, right? And so it doesn't matter whether F is algebraically closed or not for that to work. Yeah. Zariski density holds no matter what. It holds for Q. If F equals Q, this still works. And there's definitely things that are irreducible over Q, but when you extend to the complex numbers, they break up into pieces. So that's one kind of representations. These are the sort of most familiar representations. But there's others. So the other kind, the less familiar representations, these are, I don't know if there's a standard name for these, so I'm just going to make up a name. I'm going to call these things the finite order representations. And what are these? These are representations that factor through a finite group. So these are, reps, you know, so reps of, you know, you take, let's say V is a rep of a finite quotient sp2g. Let's say sp2g z mod L. You can actually always assume it's of that form, you know, L at least 2, right? This is a finite group right there. Give reps of sp2gz via the map that goes from sp2gz to sp2g of z mod L. It just reduces the entries of the matrix mod L, right? You can definitely construct representations of this. So for every L, we get a finite group, and finite groups are endowed with vast stores of representations. Okay, but these are not usually like when you first, like I think, you know, in sort of standard courses on the representation of finite groups, you never really encounter these groups. They're really complicated. So for instance, you know, let's just say, you know, just so you can give some examples of these things. For example, there is, so I talked about the Steinberg representation of SL last time. There's also, so there is, you know, there are Steinberg representations for any of these algebraic groups. So the Steinberg rep for sp2g of fp, I'll call say z mod p, p a prime, such a thing exists. These are the sort of SP analog of what I did last time. Instead of taking the sort of flags of subspaces of your field to the n, here you take flags of isotropic subspaces of z mod p to the 2n, okay? Or 2g in this case. That's one thing. So that's one thing you can do. You could look at another example. So where p is a prime, you could look at, you could let v be equal to f-valued functions on the finite set. You could take the Grassmannian of k planes inside z mod p, something like that. So there's k planes inside z mod p to the 2g. That's a thing you could look at right there. Functions on that. That's a representation. You act just because you act on this. You act on the Grassmannian. So even for projective space, that's quite interesting. So these are the sorts of things that you have. They're quite hard to. These are quite hard to classify. This second example. By the way, this is not irreducible because this contains a subrepresentation, namely the constant functions, right? So, but if you quotient out by, you take the quotient by that, you get something that's irreducible, or sometimes irreducible. It sort of depends. Depends upon k and p. It's kind of, and g. It's a little complicated. But these are these are quite hard. So these are called, so for p, for sp 2g z mod p, these are classified. So geometrically, I'm going to use the word geometrically, like I'm putting scare quotes for this audience, by what's called Kazhdan-Lustig theory. So this geometrically means, in L-adic cohomology on some variety, they're sort of this flavor. Like this is sort of arising as functions on some variety defined over a finite field, and they're sort of vaguely of that flavor, though they're quite. It's quite an elaborate theory, And for SP 2G Z mod L not prime. So these are totally wild. We know very little about them once you leave the land of fields. So these are the scary ones. As I think the takeaway you should have from this is that the algebraic representations are the non-scary representations, the ones that you like, the ones that we meet in sort of ordinary like math, ordinary like normal mathematics being like the kind that doesn't scare me, the kind that doesn't involve words like L-adic cohomology. And these representations are very complicated. You have to. They have a lot of structure. Even I should say so these are examples of finite groups of Lie type. Sort of like you take a Lie group and you replace the complex numbers by a finite field. And even for the simplest one, so GL2FP, it's not so easy to write down what the representations are. You can write down their dimensions and their characters without too much difficulty, but actually constructing, there's half of the representations are what are called the cuspidal representations, and there is no simple construction of those representations. Like they're very, even for GL2FP, they're very complicated. Okay, and for the symplectic group or GLN for higher end, they're really complicated. Anyway, so that's the sort of crash course on those. These are two kinds of representations of the symplectic group. Are there others? Well, you can do things like take tensor products of these things. But we have the following basic theorem. This is a theorem was stated finally by Lobatsky. But it builds upon very deep work of Margulis. Margulis' superrigidity theorem, which is what he won the Fields Medal for. What it says is the following. So it says the following. So let's let, so G at least 2, and let's let V be a finite dimensional rep of SP 2GZ over a field, let's just say, I'll just say a field of characteristics 0. So then, two things hold. So one, so here's a thing that's not obvious. So it's not obvious that the representations decompose as direct sums of irreducibles. For infinite groups, that doesn't come for free. Like if you're used to the representation theory of finite groups or algebraic groups, you think, oh yes, of course, everything breaks up into sums of irreducibles. But that's just not true. For general infinite discrete groups, like that's not an obvious fact. It's not true for SP2Z. That's definitely not of that form. But one higher rank, it's true. So then V is a direct sum, is isomorphic to a direct sum of VI with VI irreducible. And what's more is we can describe the irreducibles. I'll tell you what they are. So, well, we can describe them. So if we're working over an algebraically closed field, so the irreps are precisely those of the form V is equal to, I'll call this U tensor W with U an irreducible, so algebraic representation, and W an irreducible finite order representation. Okay? So every irreducible representation is the tensor product in a unique way, and it's of these an irreducible rep of each of one of these two flavors right there. Okay, so this gives a pretty satisfying picture. By the way, of course, you might ask me, what does this have to do with the symplectic group? And this is really a theorem, as you might expect from the words Lobatsky and Margulis. This is not a theorem just about the symplectic group. It works for arithmetic groups satisfying some conditions, which I don't want to give you. But it also, in particular, works for SLNZ. Or there's a version it's harder to state that works for SLN over number rings or SP over number rings. So there's, but this is the version for the symplectic group. And for SLNZ, it works exactly the same way. So it's, this is what the representation theory looks like. It's not easy to find this statement in the literature. This is not how Lobatsky actually states this in a much more sophisticated way, involving, it's like the pro-algebraic whole of these groups. There's a pro-finite part. There's a part that's some kind of some kind of algebraic group. But this is sort of what it says. I wrote, you can find notes on my website where I explain how to prove this theorem, just this theorem. Well, for SL, not for SP, but it's the same proof for SP. And I explain how to derive it from Margulis superrigidity, which is the most basic statement of this form. The most basic thing we need to control the sort of homomorphisms from lattices into other algebraic groups. Okay, yes? Where does that come from? It comes from the 80s. So I don't remember the exact date. So it's early Lobatsky. So I think it's within 10 years of his PhD thesis. I don't remember exactly what the dates are. So any other? Let's see here. OK, so that's that right there. Let me see, where am I? I'm just making sure I'm in the right place. So now we sort of know. And by the way, as I said, this is really about finite dimensional representations. In the infinite dimensional setting, which often these homology groups are, there's nothing you can say. They're just completely wild. So now, here is an example. So let's read it. So recall I stated the last time this theorem of Johnson. From the early 80s, which says that for G at least 3, we have that H1 of Torelli G1 with Q coefficients is isomorphic to wedge 3 of H, where H is equal to H1 of sigma G1 with Q coefficients. Okay, so how does this fall into our classification? So wedge 3 of H is an algebraic representation of SP 2GZ. Okay? So it falls into the nice kind of representations, the ones that we have some hope of understanding without using sophisticated technology. Okay, so now let me state, I remember I stated last time that Dan Minahan and I managed to compute H2 of Torelli. Let me state the real theorem that we prove. This is theorem, so Minahan and myself, which says that so we have that H2 of Torelli G1 with Q coefficients, so is, well, it's finite dimensional for G at least 5 and an algebraic representation of SP2GZ for G at least 6. Okay, so this is what we actually prove. And so now I said that actually we calculated it. And so the point here is that, so nota bene, before we did this, so under the assumption that H2 of Torelli G1Q is finite dimensional, which was not known at the time. Coopers and Randall-Williams computed, so the algebraic, or I'll say the maximal algebraic subrepresentation T centate of H2 of Torelli G1 with Q coefficients. And so our theorem, so this now, we now know this is everything for G is greater than or equal to 6. And they give it pretty explicitly. It's a bit of a mess, I don't want to write, I could write it down. They write it down as, I told you there's a classification of algebraic representations in terms of what's called the theory of the highest weight. So they write down all the highest weights for all the things that appear in the decomposition. There's a number. It's not a small collection of. It's not something as compact as wedge 3, right? It's a little more complicated than that. But it's in their paper, and so therefore, somehow this is the fundamental result that sort of allows us to was sort of missing to sort of make this into a complete calculation. And so this is the theorem. Now this is, as I said last time, this is not a particularly easy theorem. And so what I want to do is I want to explain the mechanism. This is the remaining, the rest of this lecture and next lecture is I want to explain the mechanism that goes into this behind this theorem right there, because the mechanism is fairly general and I think will apply in other situations as well. And it's a mechanism both for finite dimensionality and for algebraicity. And then I want to try to illustrate it not for H2 but for H1, where we already know what this is, but somehow it's, this right here is quite a difficult theorem, and so this gives a sort of, this gives finite dimensionality and algebraicity for H1 sort of by pure thought without really having to do any serious calculations. And then I don't think I'll have time to do it, but Tara Brendel and I have shown that by sort of souping that argument up a little bit more, you can actually recover this entire calculation, sort of using sort of all the information you get along the way as you prove that. So that's the story for the rest of my lectures. Before I go on to the mechanism, though, does anyone have any questions? Yes? Yeah, I also don't know if it could be finite dimensional for G is equal to 4 and 3. We just don't know, right? So yeah, so there is difficulties occurring at the primes 2 and 3 that I do not know how to overcome that would prevent me from extending algebraicity to genus 5. So it happened, 2 is the oddest of all the primes, right? And so in the end, we had to do when I explain the mechanism, like, we have to use like all this, we have to use a lot of stuff that goes into this sort of understanding and representations of finite groups of Lie type. Then after doing that, we have to do an extraordinarily large computer search to rule out small characteristic exceptions. And so getting it to work, ruling them out for g is equal to 5 seems beyond what my computers can do. Like I can do g at least 6. So, but you'll see where that is when I explain the mechanism. So are there any questions? Yes? Yeah. Yeah. So well, these are U tensor W, but if W is just the trivial one-dimensional representation, then this is an algebraic representation. So this, yeah. Well, no. So among these representations appear the algebraic representations. That's where W is just the one-dimensional trivial representation, right? And there occur the finite order ones. That's where U is the one-dimensional trivial representations. And so what you do is you take the decomposition, you throw away all the pieces that are not algebraic. That's the maximal algebraic one.
So everything that has U?
Yeah, well, everything that has a, yeah, no. It's everything that has trivial W. So algebraic means that the whole representation is just the restriction of a polynomial representation.
When you say the maximal algebraic subset,
yeah.
It means I throw away every U tensor W
where
W is not trivial.
That's right, exactly. That's what you throw away, yes.
Although there might be pieces that have...
Yeah. There might be mixed pieces, that's right. Yeah. Yeah. You throw away the purely finite order pieces and you throw away all the mixed pieces. Yeah. So, any other questions? Because we know everything is algebraic, so the maximal algebraic subrepresentation is in fact the whole thing. So, any other questions? So, anyway, let me explain the mechanism here. The mechanism has a sort of representation stability flavor. So this is sort of has some connections to the kinds of categorical things that Christine was talking about. So, though I'm going to state it in a different language. So I could make this next statement about functors on categories, but I chose not to do that just sort of for variety. I'm going to try to be a little more down to earth. And I should say, like, our theorem also doesn't really have, like, it's not just about the symplectic group. It also works for things like the special linear group over Z and stuff like that. But I'm just going to state everything for the symplectic group. OK, so here is the I'm going to give the criterion that we proved for algebraicity and finite dimensionality. And so here is a definition. So a coherent sequence of representations of SP, well, I'll say of SP of Z, I'm not specifying G because G is changing, is a sequence that looks like the following. We have, I'll say we have V1, and it's going to V2, it's going to V3, it's going so on and so forth. And then we have these maps F1, F2, F3, where first, each, V sub G is a representation. I should say there should be over a field. Over, and I could replace this with any field of characteristic 0, but let's say it's over Q, is a V sub G is a rep of SP2GZ over Q, not necessarily finite dimensional. Okay, and then we have the next is that F sub G going from VG to VG plus 1 is SP2GZ equivariant. So this G right here is the same as that G right there. So we have a representation of every symplectic group, SP1, or SP2, SP4, SP6, SP8. Yeah, G is not fixed. That's why I didn't specify. I put SP of Z, right? Yeah, I didn't specify the genus because we have all these representations, not just for one, but for all of them, just the same way that we've had in Christine's talk, right? These are things, sequence representations, but that, and there's one final condition we need here. We need that the group, the subgroup, so 1 cross SP2 of Z, which is contained inside SP2 times G plus 1 of Z, that acts trivially on the image of F sub G. So that's a mysterious condition, but I'm going to explain it. Okay, I'm going to give you an example which will hopefully make it clear why that's the right condition. No, 1 times SP2. This is just a 2 right there, right? And that's, yeah. I know, there's too many letters here, right? There's too much notation. I apologize. Yeah, OK. Each V sub G, like so V sub 3, for instance, is a representation of SP6. OK, V sub 2 is a representation of SP4. The map F2 is it's a linear map, and it's SP4 equivariant, right? It wouldn't make sense to say it's SP6 equivariant because there's, the domain only has an action of SP4, right? So that's the first two conditions right there. So we have these maps between sequences of representations of the symplectic group of increasing genera that are as equivariant as they're allowed to be. Plus, we have this final condition that, well, here, for instance, we know the action of SP4 on the image of this.
But it goes to SP4 cross 1.
Yeah, that's right, exactly.
1 cross SP4.
Yeah, that's right, exactly. Yeah. Exactly. So this right here is, I'll put this maybe right here, just to sort of put this in here. So we have that 1 cross SP2 of Z. That right there is contained inside SP2G of Z cross SP2 of Z is contained inside SP2G plus 1 of Z, right? Does that clarify it a little bit?
So this is exactly
Yeah.
disjoint from the image.
That's right, exactly. Yeah, it's not touching the image of these F sub G's. So let me give you an example. Okay, I think this will be a little clearer when you see an example. In fact, my notes told me to give an example first, but I didn't follow them, and now I regret it. So here is the example. So consider, we have the following. So let's fix D. One, and so now we have this increasing sequence of surfaces. We have, there's a genus 1 surface. That embeds inside a genus 2 surface. Like this, right? This thing right here is going to embed inside a genus 3 surface. So we have a sequence of surfaces. We keep adding a genus to the right-hand side, one after the other after the other. And so this right here, we get an increasing sequence of maps of mapping class groups. So we have mod 1, 1. We can embed that inside mod 2, 1 you just extend by the identity over the rest of the surface, right? That embeds inside mod 3, 1, and so on. Okay? So we have this increasing sequence of mapping class groups, one for each genus, right? And they're embedded one into the other. And so then we get a coherent sequence. These each contain their Torelli group. And so we get a coherent sequence. So what we do is we just take HD of Torelli 1, 1, say with Q coefficients. We get a map F1. It's the map induced by the restriction of that inclusion map into H. That should be this should be not H1. That should be HD into D of Torelli 2,1 with Q coefficients. There's F2. That's embedded in HD of Torelli 3,1 with Q coefficients. There's F3, and that just keeps on going, right? So if you look at the d homology of the Torelli group, each of them is a representation of the symplectic group, and we have it maps from one to the other. Just add a genus to the right-hand side of the surface, right? And the first two conditions are clearly satisfied. Why is this 1 cross sp2 trivially? Well, those are mapping classes supported on the thing we're adding, right? So they just commute with the image. Like, here, the image, here's the thing we're adding on this one is this genus 1 on the right. So the sp2 is just mapping classes supported on the new handle, right? And so like it just visibly commutes with the whole Torelli group on the rest of the surface. In the actions by conjugation, that's right, exactly, yeah. Okay. So hopefully this example sort of clarifies especially the mysterious last condition. That's sort of why that's the natural thing to look at. Nota bene, if you've ever seen this before, this is equivalent to this is SI of Z module. Whatever that is, SI of Z is the category of like finite rank free symplectic Z modules and symplectic maps between them. Okay, so it's like one of these sort of categorical representations of the sort that that show up in homological stability, for instance. So I think this SI of Z, the symplectic version, was introduced by me and Steve and Sam. Yeah. What example?
You take the homology of the surface.
Yes. Yeah. Oh, yeah, that's right. Yeah, forget Torelli. If we literally just took the homology of the surface, we'd get a coherent sequence, right? That is an even easier example. That's right. Maybe I should have said that first. That would be even easier, wouldn't it? So, any other questions? OK. So now let me state our theorem. So here's how you might want to prove this finite dimensionality statement. So one thing you might think about doing was trying to prove something. So when you prove things about the mapping class group, you want to sort of natural thing to do is to try to prove them by induction on the genus. Okay? I mean, when you have like a sequence of things, and you want to prove something about all of them, maybe you prove it for one of them, and you prove it for that it holds for the next one, and so on, right? That's the sort of the most naive thing you might hope to do is to prove something by induction on the genus. And so here, a naive approach to our H2 of Torelli G1 theorem. Well, it's prove it's true for, I don't know, G is equal to 5 or G is equal to 6, right? That's like a base case of an induction. And then, prove that if it holds for Torelli G1, it also holds for Torelli G plus 1, 1, right? This is like an inductive step. That's the sort of, that's like like if you asked a graduate student, what should I do? This would be like, well, what else could I do, right? You want to do something like this. And there might be some hope for this because the mapping class group in low genus, it has special properties, right? So this is, for instance, like if you want to get generators for the Torelli group, first you sort of work it out by hand in genus 1 and 2, where things are not so bad, right? You can really understand them directly because of, things are very degenerate, and then you try to prove an inductive step. So there's many theorems about the Torelli group and about the mapping class group that are proven by a sequence of steps like this. Unfortunately, what happens is like every genus is special, so every genus 3, I know special properties of it. Genus 2, I know special properties. I know fewer special properties of genus 4. And genus 5 and 6 are starting to seem like generic genera, like seem like things that are no different from any other genus, right? So like this is sort of outside the range where I would know really how to get started. And so the theorem in the next state sort of says that that you can prove this, you can do this argument, but you don't actually have to prove a base case for the induction. Okay? Let me explain. So that's what this is. So, here is a weird, a sort of strange fact is that you can do this without proving a base case. So let me explain. Let me state the theorem. SIZ, yeah, SI of Z module, right? Yeah. It's the same one. Yeah. Exactly that one. Yeah. So, I mean, I sort of, because I grew up on FI modules, right? So I prefer to think about this as the category of free symplectic Z modules and symplectic and maps between them that preserve the symplectic form.
And your last condition, what?
It corresponds to the fact that, so if you have a symplectic map, it corresponds to the fact that, let me see. Do I have someplace I can write this? I mean, it corresponds to the fact that we have these things commute on the level of symplectic groups, right? So, let me tell you, the FI statement's easier to understand, right? So if you have an FI module, I think that's that's a language that we have in common. So then if we take, let's say we take the map from M sub n to M sub n plus 2, okay? Here we have an action of Sn. Here we have an action of Sn plus 2, right? But if you take the transposition n plus 1, n plus 2, that commutes with Sn inside here, like this is, and then it fixes the image of this, right? That just follows from the sort of functoriality properties of FI modules. And it's the same condition for in the SI category in the symplectic case. Yeah. Okay, so let me state the theorem that says why we don't need a base case. So here is what we prove. Here is our, what's the stability theorem? Which is due to Minahan and myself. It says the following. So let's so V1 mirrors F1 to V2. There's F2 to V3. There is F3, and so on. Be a coherent sequence of SP of Z reps. Let's say over Q, but the field doesn't really matter. Over any field of characteristic 0 would work just fine. Okay? So we have to make, so let's make, so what I want to do is the conclusion then. So let's assume that for G greater than or equal to G naught, we have, I'm going to have two conditions here. There's condition 1 and condition 2. And I'll state the conditions in a second. Let me tell you the conclusion I want to derive, okay? The conclusion I want to derive is that once we're at G naught, these things start being finite dimensional. And once we're at G naught plus 1, they start being algebraic. Okay, and so here is, so I'll draw the conclusion, and then we'll start trying to guess what the hypotheses should be to make the conclusion true. So then we have that V sub G is finite dimensional for G greater than or equal to G naught, and algebraic for G greater than or equal to G naught plus 1. So for our theorem, of course, G naught's going to be 5, right? So what hypotheses would we need for this, right? So this hypothesis 1 is going to correspond to the sort of inductive step here. What would the inductive step be? Well, the inductive step should be something about cokernels of maps, right? That's the sort of difference. You want to look at the difference between VG and VG minus 1, okay? And so that difference is the cokernel. So the cokernel of the map FG minus 1 going from VG minus 1 to VG, so is finite dimensional algebraic representation of the biggest thing that it could be of, well, this thing right here. So V sub G has an action of SP2G. VG minus 1 has a representation of SP2G minus 1, right? And so the only thing, the cokernel, we only have an action of the smaller group, right? So of SP2. So this would be sort of like you'd think the inductive step would be. The difference, we don't know anything about them individually, but their differences eventually start becoming finite dimensional and algebraic. Okay? And now this statement right here is obviously false, as I've stated it, right? And so what do you have to avoid? Like, what counterexample, like, why do I need a second hypothesis? Well, I need a second hypothesis, and I'll say this right here. So I need some sort of finiteness condition to make this have any hope of being true. So nota bene, so you need condition 2, which I'll state in a second, to avoid the silly counterexample so each V sub G is an infinite dimensional trivial representation of SP2GZ for all G, and the F sub G is always just the identity, right? That would be the obvious, then the cokernel will be 0, right? But this conclusion would not be true. So we need something to rule out that counter. And the condition we need is that the co-invariance, we take V sub G, and we kill off the SP2GZ action. Now, you probably are more familiar with the invariance of a group acting on a vector space. You just take the things that are fixed, right? The co-invariants are like dual to that. Instead of taking the largest subthing that's fixed, you take the largest quotient that's fixed. In other words, this is V sub G modulo, you just kill off the action. So it's M x minus x, where M is inside SP2G of Z, and x is inside V sub G. So you're killing off the action in the freest possible way, right? You need that co-invariants are finite dimensional. So this right here, the trivial representation, of course, when you take the co-invariance, it does nothing to it, right? You're killing off the trivial action, nothing happens, right? So you need to rule that out somehow. But that's all you have to rule out. It's basically this stupid example, remarkably enough. So this is a theorem I will prove next time. I'm going to prove algebraicity. Algebraicity is quite hard. Algebraicity really uses delicate properties of you have to rule out these finite order representations. And that really requires a lot of delicate information about the representation theory of finite Chevalier groups. It uses everything I know about representation theory. And it uses many things I did not know a year ago, about representation theory. So that's a substantial result. Finite dimensionality, the fact that these things are eventually finite dimensional, which I think is still a pretty striking part of this theorem, That I can prove that in 20 minutes. And I will do that next time at the beginning of the lecture. So thank you.